Welcome friends to example 3. Pause the video to look at the diagram and take your time and absorb the information displayed on the diagram. Single stage means we are dealing with a singular epicyclic gear train as opposed to two or more epicyclics coupled together. Viewing the gear train from the left, counterclockwise rotations will be taken as positive. First thing to look for is the two inputs. Spot them, take note, and then put them away. We will need them at the very end. Saying that gear N3 is fixed is another way of saying its rotational speed is 0. Second input is the rotational speed of gear N5 of 900 RPM counterclockwise when the gear train is viewed from the left. Ask a friend to keep them safe for you. Now let's see what we have to solve for. Well, the first thing is that we need to figure out what the speed of the gear N1 will be. And second, we need to find out the relative rotational speed of the planet carrier. For that, we will need to know the speed of the planet carrier. So now we apply what I call my table drill to solve this problem. Columns 1, 2, 5, and 6 are super easy and require no brain cells at all. So let's fill them up first. Column 1, just list all the gears in the drivetrain. Even though N2 and N4 are actually a compound gear, list them separately. Include the arm as well. Column 5, equal signs in every cell. Column 6, the rotational speeds of all the gears and the arm. Just the labels. Column 2, give every gear X RPM. First, we do column 3. There are essentially 3 activities that we do in column 3. Of key importance is the act of transforming our epicyclic gear train into an ordinary one. We do this by locking or freezing the arm. Note, the arm is also sometimes called the planet carrier. Now that we have locked the arm and we have an ordinary gear train to work with, our next task will be to compute the gear ratios of this ordinary gear train. To do this, we must overlook and ignore any existing rotational speeds given in the problem. And this is why you will ignore omega N5 of 900 RPM and omega N3 of 0 RPM. We are now in a position to compute the gear ratios of the resulting ordinary gear train. Start with the arm and lock it or freeze it. In other words, omega arm is set to 0 RPM. With the arm locked, we are now left with an ordinary gear train consisting of gears N1, N2, N3, N4, and N5. To compute the gear ratios of this ordinary gear train, give N1 gear an unknown number of turns and compute the rotational speeds of the remaining gears one by one. To compute the rotational speeds of the remaining gears, you will need to know the tooth numbers of all the gears in the drivetrain. So N2 meshes with N1. N1 is a driver, N2 is a driven. Number of teeth as shown on the diagram is quite simple. We take the rotational speed of N1 and multiply it by a fraction. The numerator will be the number of teeth of N1 and the denominator will be the number of teeth on N2 As simple as that. And of course, there's a minus sign. That is because they are rotating in opposite directions from each other. From N2, we go to N3. So N2 meshes with N3. We just have to be careful. N3 is an annular gear, so it will rotate in the same direction as N2. We take the rotational speed of N2 and multiply it with a fraction. The numerator will be the number of teeth of N2 divided by the denominator, and that will be the number of teeth on N3 gear. There is a plus sign because both N2 and N3 are rotating in the same direction. For N4, just copy paste the rotational speed of N2 because they will be identical. N2 and N4 together combine to make the compound gear. So that's what we do. We just copy paste N2 in the N4 cell. Next, we do N5, which is again an annular gear, and it meshes with N4. So we take the speed of N4 and we multiply it with a fraction. The numerator will be the number of teeth on N4 gear, and the denominator will be the number of teeth on the N5 gear. And that's it. We are done. We have completely populated column number 3. Before moving on to column 4, we just clean up our algebra. And that is what you see in column 3. I just simplified the fractions. In column 4, simply take the stuff you have in column 2 and add it to the stuff you have in column 3. Now clean up the signs, and there you have it. Column 4 is complete as well. From the completed table, we now extract the equations that will lead us to the answers we are looking for. To reveal the equations, we simply get rid of the first 3 columns. Equations show us that if we could somehow solve for x and y, we would be in a position to find out the rotational speeds of all the gears in the gear train. In order to figure out x and y, we retrieved the 2 inputs we had set aside. We replace omega n5 with plus 900. And we replace omega n3 with 0 RPM. And this gives us 2 equations with 2 unknowns, x and y. With the x and y known, it's super easy to find the rotational speed of gear N1. We just add the values of x and y because that is the equation we have. So the rotational speed of gear N1 is x plus y. To answer part 1, we retrieve the equation for omega N1 and simply enter the values for x and y. The answer turns out to be a positive number. Based on the convention we chose, positive value means that gear N1 is rotating counterclockwise when the gear train is viewed from the left. Now we are ready to answer part 2 of the question. It's the relative speed we are after. We already know omega N1. We can calculate omega arm. With these 2 known, we can calculate the relative speed. Yes, it's a vector equation, but since all vectors point along the z-axis, we will just use the magnitudes to do the computation. So let's first compute the rotational speed of the arm. Rotational speed of the arm is a positive number, indicating that the arm also turns counterclockwise when the gear train is viewed from the left. Now we have all we need to compute the relative rotational speed of the arm with respect to gear N1. So there we have it, the answer to part 2 of the question. So even though the arm's absolute rotational speed is 3,471.4 RPM counterclockwise when the gear train is viewed from the left, to the observer bolted to the gear N1 and rotating with it, the arm appears to be rotating at 8,678.6 RPM clockwise when the gear train is viewed from the left. I do hope that you enjoyed the video. Stay tuned for more.